All right, so we're going to take a look at the start of section 5.1, which is on polar coordinates. So polar coordinates are a different way to write coordinates. This is the kind of system we're used to, right? XY axis. This system works great as long as you're graphing things, if it's like 2, 4. Very easy to graph that. Right 2, up 4. Well, the real advantage to this system is when you start graphing things more complicated than points, it does things that are straight pretty well, like lines. Those are the only things that are straight. So lines are like the easiest thing to draw on this kind of system. What can be kind of hard on this is things that are curved, especially circles. Circles are not very easy to draw in this kind of system. But if we use a polar system, then circles become a lot easier. All right, so just what I just said. We've used XY coordinates for graphing. We can also use polar. So polar graph paper looks a little different. Okay, instead of having like a grid, horizontal and vertical lines, it has circles. Okay? And what we do is we move out a certain number of circles from the origin. And you can move in between, like you could move out 2.5 circles, things like that. So you can go with decimals just like you can with XY axis. And I'm going to come right back to this, but I'm just going to show you there's a bigger version of polar graph paper. So the center is called the pole, not origin, and it's labeled in degrees, okay, starting at the positive x-axis, going counterclockwise. 0, 90's at the top, 180, 270's at the bottom.
Does the pole always have to be in the origin?
Yeah, the pole is like the origin, yes. Yep. Just a different name for it in polar. And what I'm going to do is I'm going to draw a circle on a graphing calculator, show you how challenging it is to do a circle using XY coordinates, and then I'm going to show you how easy it is to do it in polar. All right? Yeah?
Don't you technically have to have an infinite amount of variables for it to be a circle with the XY?
Well, you'd graph an infinite amount of points if you want to think of it that way. Just like graphing like y equals mx plus b. It's a line with a slope of m and a y-intercept of b, but you don't really graph an infinite amount of points. We just draw it as a solid line. Yeah. All right, so let me show you the equation of a circle using the system you're used to. Okay, y equals kind of stuff. If I want to graph a circle, I have to start with this. The square root of, and I got to pick how big of a circle I want. So let's do a radius of 4. So r squared. I can make r anything I want. Depends on the size circle I want. Minus x squared. Now, if I draw that, watch what happens. Let's go zoom square. Okay, I get part of a circle. And you can tell it goes up 4 units from the origin. But the problem with this is I don't have the whole circle, because circles fail the vertical line test. This calculator can only draw functions, right? If you put a vertical line, it would hit a circle more than once. So the only way I can draw a circle using the y equals is I kind of have to cheat and draw the top and the bottom half separate. So I can put that in. And then the negative of it would give me the bottom half. So 4 squared minus x squared. And that's the best I can do. It doesn't even connect. It should connect. But what happens on the sides of the circle is it's getting so steep, the calculator has trouble when things get steep in that part. So it can't connect it. But the point is I had to type in all that stuff just to draw a circle with a radius of 4. Okay? Now, instead of graphing things as functions, let me switch it to polar. So what I'm going to do is I'm going to change from using an xy axis to now this new system I'm showing you, polar. Notice it doesn't say y equals anymore. Now it says r equals, because things are based off a radius in polar. They're not based off an xy coordinate. All I have to do is type in 4 and hit graph, and there's my circle. So the point there is so much less stuff I had to type in. I had to type in one number to get a circle versus having to type in all of that stuff to get the same picture. Just pretend the sides were connected. All right? So it's kind of like using the right tool for the right job. Polar is really, really good to draw things that are circular. Polar is really hard to draw things that are lines. Okay? You can do it, just like I can do circles in this mode, but each mode has things it's good for. So we try to use the right thing when we have to draw certain types of pictures. We're never really going to be doing fancy sketches in polar. The most we're really going to do is graph coordinates. If we spent a second week on it, we would get into all kinds of sketches you can do in polar that are all kinds of things, like spirals and other things you've never seen. But we're just going to be graphing points, so it's a lot easier. So a point in polar is still written with two numbers, but it's not an x and a y. It's a radius, and it's an angle. That's what the r and that's what the theta stands for. And I'll show you how you graph in a second. Yeah.
Is there never a negative radius, technically?
It's kind of weird to think of negative radius, because if you think of radius as distance, distance can never be negative. We have a way of sketching something if the radius is negative. It's just like moving right instead of left or left instead of right. It's kind of like an x. R is very similar to x. You start by moving left or right a certain number of units. So when I do this, I try not to think of it as like a negative distance. I try to think of it as, oh, negative r just means distance to the left instead of distance to the right. That's how I think of it.
What's the difference between the way it looks?
I'm going to show you, we're going to go through all the different cases, like a positive and a positive, a negative and a negative, negative, positive. We'll do each one. Again, we're only going to be graphing dots, so you're not going to see like fancy spirals and pictures. You're just going to see single dots. All right, so again, r is the distance from the pole, and theta is a certain amount of degrees or radians that you move. So, I said r is kind of like x. You start at the pole, and you move out the number of rings indicated by r. If r is a decimal, you go in between rings. Now, if it's like x, that means which two directions could you move in? Think of what you would do for like the x-axis. Yep.
Left or right?
Left or right. What's going to control if you move left a certain number of units or right is a positive or a negative. So if r is greater than 0, I mean, you could really shorten that up. You could just say r greater than 0, move right. Or if you want to write it all out, if r is greater than 0, move from the pole to the right. If r less than 0, move left. All right. So yes, it is kind of weird to think of that, like how can r be negative because it's a radius, radius is distance. But I think of the negative as telling me a direction, not negative distance. Tells me left. All right? And that's the first part of the coordinate. So you're not done. It's like if you graphed an xy coordinate, you've done the first part. Now, from here, you're going to move a certain amount of degrees. Now you're moving in a circular pattern with the degrees. Okay, you're following the circle. When you move on a circle, you don't really describe it as left, right, up, and down. What are the two directions that you can move on a circle? Yep.
Clockwise and counterclockwise?
Yep, clockwise and counterclockwise. Which direction you move is going to depend, do you have a positive or a negative angle? If you have a positive angle, okay, greater than 0, counterclockwise. So positive is counterclockwise. And if you forget, just think of it this way. That's the opposite way that a clock goes. If you have a negative, clockwise. It's the other way. So after you move out the number of units that R tells you, and then after you move clockwise or counterclockwise, you put a dot and you're done. Again, sketching entire pictures is a little more work, and that's why we're not really getting into that. We're just focusing on graphing single points. But if you want to see real quick, I can just show you like a neat picture you can do in the polar system that you can't do in the y=, system. Right, so this is a simple one. That's just a spiral. And I could make it spiral as many times as I wanted. That's one revolution of the spiral. I could also do something like 5 cosine 4 theta. Watch what this looks like. So I put a 4 in there, 4 theta, and I got 8 petals. So there's patterns here, like how many petals you get and how long each petal is. So things like that you can't really do in y=, right? Because that definitely fails the vertical line test. But all kinds of interesting graphs you can do in polar. All right, so let's just practice graphing some points. And we'll try like every different case we could have. Now, if you don't have polar graph paper in front of you, you didn't bring your polar graph paper to class today, that's okay. Just, you can pretty much just go like this. You thought about it? Yeah, me too. And then, like, if you have to do this in the homework, you don't have to draw the same graph over and over. You could just put something like this and say that was number 8 in the homework. Something like this, that was number 2. Use the same grid over and over. Number 6. So you can put all your problems on one grid, you might have to draw it by hand. If you Google it, you can Google polar graph paper and print it out. But I mean, you're only going to need to draw the grid one time, so it's not that bad. Yeah, you could do the same thing with your notes. You could just put example 1, example 4, if you want to copy them, or just make your own grid for each problem. It doesn't take that long. All right, so let's just start with the R and the theta. What's R here? 3. And theta? 120. Now, theta can be in radians. Most people have an easier time if they change degrees to radians to degrees. But I don't care how you do it as long as you put the dot in the right spot. So, R is positive. So I'm going to start from the pole and move 3 units which way? Left or right? Yep. To the right. Now what I'm going to do, I'm going to erase this in a second. I'm just temporarily going to put a little mark there. That's not the answer. But that's where I'm going to start moving 120 degrees from. So I went 3 to the right, which I'm going to erase that in a second. And now I got to go 120 degrees. Which way? Clockwise? Counterclockwise. Let's see. Positive is counterclockwise. I just have to think about it for a second. Now on my grid, each radial line coming from the center is 15 degrees. They don't have to be set up like that. You can draw more or you can draw less. But that's how my graph paper is. I'm not going to label all of them, but you get the idea. So I got to go 120 degrees. So how far past 90 do I have to go? How many degrees?
30.
I got to go 30, and each section is 15. So I got to go 2 more past 90. So follow that line, go up to 90. That's 15 more, that's 105. Another 15 gets me to 120. And that's it, that's your answer. So right 3, 120 counterclockwise. Any questions on that one?
Oh, so the R is just how many like rings?
Yep, and you can move either right or left, and that's your starting point once you do that part. So like if this was a -3, I would have started from here, and I would now move 120 degrees in the same direction. So I would ended up over there. So basically, when you put a negative in front of the number, it kind of puts it on the other half of the circle. That's where it ends up. Right, but we'll practice more with those. All right, let's try this one. What's different about this problem? Joe?
It's in radians.
It's in radians. So if you want, you can change that to degrees if that's easier for you. That's a common one. Does anyone remember what pi over 4 is in degrees? 45, yep. That's a 45. Now it's exactly the same setup. Positive radius, positive angle. So Ephraim, I'm going to start by going 5 units which way?
Right.
To the right, yep. So 1, 2, 3, 4. Again, I'm just going to put a temporary mark there that I'm going to erase. And now I'm going to go 45 degrees. Dylan, clockwise or counterclockwise?
Counterclockwise.
Yep. So 45 is halfway between 0 and 90. So 15, 30, 45. That's it. Questions on that one? Okay, so that's a positive radius, positive angle. Let's look at positive radius, negative angle. All right, so nothing you have to change to degrees here, so that's good. So we're starting with a 5, and that's the same as the last problem. Okay, so 5 units, right? And now I'm going to go 210 degrees. Which way? Clockwise. Well, if I went halfway around, how far is that?
180.
That's 180. Then how far is 210 away from 180? 30. So I got to go 2 more sections. So clockwise, 1, 2, I end up right there. So I went halfway around to 180, and then I went 30 more to get me to 210. Any questions on that one? So that's a positive radius, negative angle. I'm not going to do every single problem in degrees and radians. I'll give you an example of all the positives and negatives, but keep in mind, any of these angles could be in radians. All right, so this one's a radian, and now it's a negative radius, positive angle. Not necessary, but we might want to change that pi over 2 to degrees. What's pi over 2? Yep. 90. All right, so I'm going to start out by moving 3 units, and I'm going to go 3 units which way? Yes, 3 units left. I'm going to put a temporary mark there. Now I'm going to use that as my starting point, and I'm going to go 90 degrees from that temporary mark. I just have to know 90 degrees which way. Clockwise or counterclockwise? Counterclockwise. So counterclockwise, it's like going down in this case. Okay, opposite way a clock would go. So go 90 degrees, and you end up right there. This time, I'm going to draw how we got there, okay? Because I want to look at this one a little closer. Okay, you don't have to draw that, but I'm going to show you. I want to show you something right now. Can somebody give me a different coordinate that would get me to exactly the same spot? Joe?
-3, 200, and whatever the other. I can think 270.
All right, so he's thinking -3,
Negative 270.
negative 270. Okay, let me try it. So -3 means I'm going this way, and negative 270 means I'm going to go clockwise 3/4 of the way around. That's 270, 3/4. So he went that way. Yep. So that's another way to get to that point. What's another way? Yep.
3 negative 90.
All right, let's try it. 3 negative 90. So now we're doing one where we're going to go right first instead of left. So 3 negative 90. Yep. So if you look at the pattern here, we have the negative, positive, positive, negative, negative, negative. The only one we're missing is the positive, positive. So can anyone tell me what the positive, positive would be? Yep.
3270.
3270. So right 3, 270. Okay. Which one is correct? All of them. They're all different ways to get to the same point. So in polar, there are 4 basic ways to get to every point. Doing something like this, like if you went right and then went around, it didn't stop, and then went around again and stopped, that doesn't really count as a different way. Because if you count that, I mean, you could just go around 12 times and then stop. So the 4 basic ways are right, clockwise, left, clockwise. Right, counterclockwise, left, counterclockwise. So you can go left or right, then clockwise or counterclockwise. So it gives you 4 options to get to every point. Why do I show you the different ways if they're all correct? Because if you're doing a problem and it's a multiple choice, and we're doing some kind of calculation, and let's say you figure out an answer. Let's say you get this answer, but you're doing a multiple choice question, that answer isn't listed. Maybe that one would be listed. You just have to understand that what you found is exactly the same as what's listed. So you might have to change your answer. If you get like a negative in there, maybe they wrote the answer with positives. Okay. So any questions on that? And that's something you'd never see in this system. Like, can somebody give me another coordinate to get to that point? Is there another one? No. If you want to get to that spot, it's 2 to the right, it's 4 up. There is no other way to get to that point. If you give me any other numbers than a 2 here and a 4 here, it's not going to get you to that point. All right, so that's something that's a little different in polar. All right, let's do that. Let's look at this one. We kind of just did a negative, negative in the last problem, but we'll try. We'll try one more. All right, so what am I going to do here? I'm going to start out by going which way?
Left.
Left 2. So put a mark there. And now negative 180 degrees. Negative angles go which way?
Clockwise.
Clockwise. So technically, I'm going this way. If I went the wrong way, what would happen in this problem?
Still the same spot.
It wouldn't make a difference because 180, negative 180, that's halfway around either way. So, again, technically I followed the dotted line. I went clockwise. Now, we studied this before, but what did we say you can always add to an angle? And it doesn't change where you land. 360. So technically, if I take negative 180 and add 360 to it, that's exactly the same point. I could also take 180 and add 360 again. What was it? Negative 540. That's the same point. It's just making an extra revolution.
No.
Question? Justin, question?
Oh, no, you're good. You keep going.
900, 1260. These are all the same coordinate. I can add 360 as many times as I want. It just has me going around more times. All right. So keep that in mind. If you get an answer that has a negative angle, a quick way to make it positive is add 360. Or if you get a positive answer and they wrote it as a negative, you can subtract 360 from your answer. Okay. For me, though, I'm visual. I need to kind of see it. So if you ask me to write a coordinate in different ways, I like to just put it on a grid and then just like trace it with my finger which way I'm going. And that's okay, we'll try this one too. 0, 300.
Just be like a line. Not a line, but like just straight down, like straight to the sides.
Stay in the middle.
So you're staying at the pole. You're not moving left or right. But then what are you doing? Yeah, you're just staying in place. So it would look something like this. Start by putting a temporary mark at the pole, but then you have to spin it 300 degrees. About like that. So just make sure that you spin it. Right? You spin it.
Wait, this is a joke, right?
No, on the test, the way you do it is you put your pencil down, and then you just spin it.
Nah, yeah, you're playing with me.
So the point is 0, comma anything is right at the origin. Never moves. Okay, it's always at the origin. You can't really tell if you've gone 600 degrees or negative 1,000. It stays right where it is. How about if I put the 0 in the second spot? Is that going to stay at the origin?
No.
No. That's going to move 1 unit to the right. So if you have a number comma 0, it's always going to be horizontal, right or left. Okay. So we've done every case you can have: positives, negatives, and then zeros in there as well. All right. So now what I want you to do is the same thing that I kind of did in this problem right here. I'm going to give you a coordinate, 3 comma pi over 6, and I want you to write it 3 different ways. One way I want you to do it is with a positive radius. So I want the first number positive. And I want the angle to be between 360 and 720. So you might have to make the angle bigger in this problem. Okay, we just talked about how to do that. The second way I want you to write it is I want the first number to be negative. So I want a negative answer. And I want the angle positive between 0 and 360. Okay, and then the third way, we're going to go back to a positive radius. Now I want a negative angle between negative 360 and 0. Right, so the easiest thing might be to make a sketch and do what I did in the 4 different colors. Okay, but that's try that. I'll give you a minute or 2 to try that, and then the last thing we're going to look at is how do you convert between the kind of coordinates that we're used to, x, y, and a coordinate in polar. So if I just give you the numbers, how do you change one to the other without doing any drawing at all? We'll practice converting one way today, and then we'll pick up converting the other way tomorrow. Okay, so first thing I would do here is I would change pi over 6 to a degree, just so I can kind of figure out where it is, because I can work in degrees in my head easier than a fraction with pi. What is pi over 6 in degrees? 30. 30. If you think of pi as 180, it's 180 divided by 6. All right, so let's mark where that is. 3, 30. It's right there. All right. I only have 2 choices for the number that I put in this spot. If you put a number other than one of these 2 choices, you will not land on the right circle. So what are your two choices for numbers in the first spot? 3 and -3. So I can pretty much answer the first part of all these coordinates. All right, you want to answer greater than 0? I've got to use 3. You want a number less than 0? I'm going to have to use -3. Another one greater than 0? It's going to have to be 3. If you don't put 3s or -3s, you're going to land on the wrong ring. All right. Now they want an angle that's between 360 and 720. So all I have to do is make that angle bigger. What can I add to 30 to make it bigger?
Yep, 360.
I can add 360. So if I add 360 to 30, basically I'd be doing this. Going around an extra time and stopping. What's 30 plus 360?
390.
390, yep. So there's the first way. Okay, second way. They want a negative radius, but a positive angle. So, negative radius, that's your start point. Positive angles go which way? Clockwise or counterclockwise? Yep. Counterclockwise. So in this case, starting from that point, that's kind of like going down. So you're going to go this way. So we just have to figure out how many degrees it is to get over to that part. Well, it's halfway, and then it's 2 more sections. So just add that up. Yep.
210.
210. Yep. So -3, 210. All right, so that's that one. Oh, I'm just going to erase it. And now the last way, well, I can start with the negative right away because they want a negative angle. And I'm starting 3 units to the right. Negative angles go clockwise. So, actually, I'm starting right here. So, we're going to go right and clockwise. So it's like I'm taking the long way to get all the way over. So what angle would that be? Negative, it's 2 sections shy of going all the way around.
330.
Negative 330. Because each section is 15, so it's 30 degrees shy of all the way around. And that's it. So we've written this point 3 different ways. Questions on that? Okay, so last thing we're going to look at is converting from polar to rectangular. All right, so let's say we have a point in polar. It could be anywhere. I just put it in quadrant 1. I didn't draw all the circles in. In fact, the book in the homework, they don't always put the circles in either. So if you want to put the circles in, like on your notebook paper, that's fine. So this is your R. What is it in this problem? I don't know. It's R. It's just a certain distance from the origin. Now, what I'm going to do to figure out rectangular is basically starting with this. Rectangular doesn't use R and theta. What 2 letters does that use? The way we're used to graphing. Yeah. Uses X and Y. And it's called a rectangular coordinate system. So I want to get rid of the R and the theta, and eventually I want to have an X and a Y. And I'm going to use that diagram to do it. Okay. Theta is right there. That's your angle that you moved from the x-axis, positive x-axis, to that line. Anyone have a thought at what I can add to this picture that will help me to figure out a horizontal distance, which is x, and then a vertical distance, which is y? So that's what I want to figure out, a different way to get to this point by moving horizontally and then vertically. That's how x, y works. Yep.
Could you do the diagram? Draw a line from R down.
Okay, so let's start with that. Let's draw a line from r down. So now, is that straight? Yeah. I just made a right triangle. So when you're talking about an xy coordinate, and you move from here to there, what number or what letter tells you that distance in an xy coordinate? X tells you from the origin, move left or move right, a certain number of units. So that's your x. And then from there, we're going up. What letter in an xy coordinate would give you the length of that segment in blue? That's your y. So what we have to do is just figure out a formula for x and y based on knowing r and theta. Okay, so that's what we're going to figure out. So I've got a right triangle. Let's start with x. We're going to figure out the names of the two sides that I know, but forget about y for now. So we're focusing on, that's what you want to know. They'll give you that in the problem, and they'll give you that in the problem. Always give you the r and the theta. What's the name of the side that's right next to theta? Is it opposite, adjacent, or hypotenuse? Yep. Adjacent. So the adjacent side is what we want to know. And r is the radius, but it's also the what in the triangle? It's the hypotenuse. So I need a trig function if I'm trying to find x that has adjacent and hypotenuse in it. Which trig function has those two? The choices are sine, cosine, or tangent. Yep. Cosine. So let's set up a formula. The cosine of my angle, which again they're going to give me, I don't know it, I'm just writing it as theta. But the cosine of my angle equals adjacent over hypotenuse. So Christian, which side is adjacent here?
Theta?
To theta, yes. Which side is adjacent to theta? X. And which side is the hypotenuse?
The radius, r.
R. So there's my formula. I will know theta and r in a real problem, and I will fill them in. But I want to get r by itself, x by itself. So what would I do on each side to get x alone? Yep, Scott? So we have divide by r now. We want to get rid of the dividing by r. Yeah, multiply by r over 1 or even just r. So just multiply both sides by r. You have a divided by r and a times r on the same side. They cancel out. So now all you have on the right-hand side is x. And on the left, you have a formula that will give you x. So if you want to know x, you take the cosine of the angle they give you and you multiply it by r. That's how you would convert polar to the x value in rectangular. Now we need one more formula to convert polar to the y value. All right, so we'll do the same thing again. This time, I'm focusing on that side and the r. So r is still hypotenuse, so I'm still using that. But what is y? What side is that?
Opposite.
Opposite, yep. So now I need a trig function if I want to find y that has opposite and hypotenuse in it. So which trig function would have opposite and hypotenuse?
Sine.
Sine. Yep. So we're going to set up our equation just like we did before. Sine of my angle equals, and what's going to go on the right-hand side? Yeah, Christian.
Y over r.
Y over r. We're going to do the same thing we just did. We're going to get y by itself, and there's our formula to find y. So what's going to go on the left-hand side of that equal sign?
R.
Yep, part of it.
R sine theta.
R sine theta. Yep. So if you want to convert a polar coordinate to the y value, you use r sine theta. To convert a polar coordinate to the x value, it's r cosine theta. And I think I have that all written out right here. That's the same thing you just wrote down. Okay. So if you have a point in polar, they give you the radius, they give you the angle. Use the following two formulas to convert polar to rectangular. Now, out of the three trig functions we use a lot, which one didn't I have to use at all?
Tangent.
Tangent. Well, tangent's going to come in when we want to go back. So when we look at it tomorrow and we want to change rectangular polar, you're going to see tangent come up. And what other formula didn't we use that you use a lot with triangles?
Inverse.
Inverse tangent, so that's a good point. It's actually going to be inverse tangent that we use tomorrow. But there's one other formula involving the sides of triangles. We didn't use the Pythagorean theorem. That's also going to be used when you want to go back the other way. Right? But for today, you just need what's in that box.
My honky go up a little.
So they've given us a point. The angle is in what? Radians, but that's fine, because all I have to do is, if I'm just plugging it into a formula, just make sure I change my calculator to radians. I'm not trying to sketch this by hand, so it's not like I need to visualize what pi over 6 is. I just need to plug it into a formula. So I'm just going to remember, change my calculator to radians for this problem. It could have been degrees, but it's not. Okay, so can somebody tell me what the calculation would be for x? Just filling in my r and my theta. Yeah, Scott?
6 cosine pi over 6.
6 cosine pi over 6. And how about the calculation for y? Yep, Derek.
30.
So what would be the whole thing?
Oh, 6 cosine 30.
Okay, I'm just going to leave it as pi over 6. Even though it is 30, if your calculator doesn't do radians, then yes, you would have to change pi over 6 to 30. Okay, so let's plug them in. So we've got 6 cosine, I'm already in radians, so that's fine. Pi over 6. And for the first one, I get about 5.20. So that's about 5.20. And let's do 6 cosine pi over 6. Let's actually try sine. So when you're doing the y value, you want sine. I wrote the wrong one. So 6 sine pi over 6 gives me 3. Okay. So the coordinate in rectangular is 5.20, comma 3. Okay, any question on that? Now that's writing it as a decimal. You might see it written a little differently on a text. Let me show you what you might see. So that's 3 over 2. So 6 root 3 over 2, which would be 3 root 3. Might see that on a test. Now, if you're looking at that, well, you might be like, how did he get 3 root 3? Well, what I did is I took the cosine of pi over 6. Pi over 6, Derek told us, was 30. Any angle that's a multiple of 30 or 45, we have a nice way to write the answer. So remember that I gave you a chart. It was like a few weeks ago. But there was a chart and it had all these square roots of 3s, square roots of 2s. People remember that chart with all that numbers on it? Basically what I did is I recognized 0.866 is one of the numbers in that chart. Okay, there's a few, there's like 4 or 5 that if you know them, you know that whole chart. So that chart I gave you, I basically have that 4 or 5 numbers on it memorized. Okay. 0.866 is always root 3 over 2. So I knew that this part is root 3 over 2 times 6. 6 root 3 over 2. All right? The easy way, if you don't remember the numbers in that chart, is if they give you an answer like this, and you get 5.2, just take the answer they got, 3 square roots of 3, change it to a decimal, and see if the decimal matches yours. Okay? That's the easiest way to do it if you don't remember the chart. Okay? Just take the number they gave you, type it in, get the decimal, see if it matches your decimal. Okay? But that definitely will come up on the test, and you would probably see it written this way. So, any questions on how to change that to a decimal if you need to? Or memorize that chart like I did. Those are your 2 options to figure that out. All right, so I want to look at graphing that point, and I'm going to show you something I can do on here to check my answer. So the original point was 6, 30 degrees. 1, 2, 3, 4, 5, 6, 30. Okay, I'll let you double check it, but does everyone agree that I graphed that in the right spot? 6 to the right, and then 30 degrees counterclockwise. Anybody think that that point is wrong? Okay. What I'm going to do is I'm going to leave the point exactly where it is. I'm going to replace the background behind the point. I'm going to replace it with a rectangular grid. If I've done this correctly, it should look like that point is a little more than 5 units right and exactly 3 units up. All right? So it's kind of like the background is going to change behind it, but the point is going to stay in the same spot. All right, so let's see what happens. Now I've got to use the same graph paper scale because they make bigger and smaller graph paper. I think that's the large. Let's try it. Okay, so I changed the background behind it to rectangular, so it's like I instantly just converted it to rectangular. Does it look like that point is a little more than 5 units right and exactly 3 units up? Yeah. So again, it's not really something you can do on your notebook, but it just shows on the computer that it is exactly the same point. I converted it correctly. All right, any questions on that one? All right. Okay, so let's finish up with this one. I'm not going to change the background and show you again, but let's just write out our 2 formulas. What would be my formula, Oscar, what would be my formula to find x?
R cosine. You want me to actually?
Yeah, you can fill it in, sure.
So it's -4 cosine 120.
All right, and my formula to find y is going to be -4 sine 120.
Yeah.
Now, is 120 a multiple of 30 or 45? Is just yes or no?
Yeah.
Yeah. 120 is a multiple of 30, which means the answer to this on the test, you would probably see a square root in the answer. If you don't like the square root, change the answer to a decimal if it's a multiple choice question, and match it with whatever we're about to get right now. Okay, so let's see what we get. -4 cosine 120. We get about -3.26. So that's the x. And for the y, -4 sine 120. Oh, gotta be careful. What did I do wrong? Yeah.
You're in radians.
I'm in radians. Okay. This problem has the little circle. So that's actually a good mistake to make because some people do that on the test. It has the little circles on it. All right. So that means I should have done this in degrees. The reason I knew I was wrong is because usually if an angle is a multiple of 30 or 45, especially the 30s, actually multiple of 30, one answer comes out nice, one answer comes out messy. I was getting both answers coming out messy. That shouldn't happen when you have angles that are multiples of 30. Okay, one's nice, one isn't. So let me just type it in again. So -4 cosine 120, there's my nice answer, 2. So that means if that's the nice answer, the next one is going to be the messy answer. -3.46. Okay, so final answer, x, comma, y. You're going to see that written as a square root on the test. There is a nice way to write that with a square root. But change that square root to a decimal if you can't figure out what it is, and then match it up. Okay. Does anyone need me to do that on this one, or is that okay?
Yeah, do it real quick.
Do it real quick? All right, so let me figure out what it would be. The sine of 120, there's that 0.866 number again. Okay, there's only like 4 of them that come up. I just have it memorized. 0.866 is root 3 over 2. So this is root 3 over 2. And there's a -4 in front. And then that would reduce. So that would be 1 and 2. So that number that's underlined on the test would look like this. -2 square roots of 3. That's the exact answer. But if you're like, wait a minute, I got -3.46, that doesn't look the same. Well, hold on, just type it in. -2 square root of 3, that's what they had on the test. And that's -3.46. It's exactly the same decimal that you got. Does that make sense?
Yeah, I mean.
Yep. Okay, and you can't do that all the time. You can only do it if the angle is a multiple of 30 or 45. Okay. Okay. So any questions on converting from polar to rectangular? Okay, so tomorrow we'll look at the other way, which is converting to polar instead of to rectangular. And that'll finish up section 5.1, and then we'll start looking at a section in the back of the book, which is complex numbers. Okay, so homework tonight, it's all evens, and it's 12 to 26 and 40 to 46.